Thank you, guys. Thanks. So, my name is Sampanis. I'm working as a security researcher at CENSS. I'm doing their vulnerability research, reverse engineering, and exploit development, focusing on Windows kernel. So this presentation is actually split in two parts. On the first part, I'm going to discuss about a bug that I found some time ago, a mitigation added to the GDI objects using push logs, and two ways to bypass this mitigation. And on the second part, I'll present the Win32k filter for the Edge browser, GDI primitive characteristics, and their future in RS4. So, in early July of 2017, I was writing an exploit for that CV. The vulnerability was documented in a blog post by Nicolas Konomo without a proof of concept, but it was very detailed though. And I quickly realized that the bug was, that the vulnerability was reintroduced, and actually that the Windows 10 RS2 was still vulnerable. So since the bug has been explained by a couple of researchers, I will try to explain it very briefly. Please also note that this presentation is full of code snippets, and all of them are a production of reverse engineering. So let's see a few things that you need to know in order to understand the bug. So a GDI path object is used to store coordinates for drawing. Okay? So we can create a path object by calling the system call ndgdi begin path. And we can store coordinates to that object by calling functions like move to x, line 2, polyline 2, etc. And here's the definition of move to x. It takes 3 arguments. The first one is a handle to the device context, and the other two, the x and the y, are actually a coordinate. So the path object is using a data structure called pointFix to save a coordinate. And in case we need to store multiple coordinates, a data structure called path record is used, which is actually a double linked list of point fixes. So the number of how many coordinates we have stored so far in a path object is saved in an integer called ccurves. All right, keep this in mind. So there is a similar object that also stores coordinate. It's called region. It's also a GDI object. And each coordinate in the region object is saved in a data structure called edge, which is the following data structure. So we can actually convert the path object to region by calling the system call ndgdi path to region. And the conversion is based on the allocation of edges of the region object, based on the integer that exists in the path object. So here is the pseudocode for making things clearer. So as you can see, from the path object we receive the ccurve integer that has the number of how many coordinates we have stored so far. And as you can clearly see, there is an integer overflow on the allocation of the P3 edges, which is the data structures for the region. And later, in addEdge to get, a heap overflow takes place. So I wrote a proof of concept. I tried to write a proof of concept for RS2, as explained, and I got a kernel panic. And the reason was a mitigation added in the GDI handle manager at Redstone 1. So let's see a few things about the GDI handle manager. So the main goal of the GDI handle manager is to store a GDI object in the handle table and to return a handle for that object. Also does the opposite, takes a handle and translates that handle to a kernel object address. And in order to do that, it consists of a couple of data structures. So the core data structure is the GDI handle manager, which contains a pointer to the GDI handle entry directory. The GDI handle entry directory is allocated in the GDI handle entry directory create, and it contains 256 pointers of GDI handle entry table. Now, the GDI handle entry table is allocated in GDI handle entry table create, and it contains 2 notable members. The first one is the shared memory cell data, and the other one is the entry data lookup table. Now, for each newly created GDI object, a GDI cell 64 data structure is created, which is actually the metadata for that object. It contains information like which process has created that object. And the shared memory cell data is actually an array of GDI cell 64 data structures. And it is called shared because it is actually shared between the Win32k component and a GUI process. Now, usually as a GUI process, we define every user space process that loads the user 32 DLL or GDI 32 DLL. And every query process has a copy of shared memory cell data in the process environment block in the member GDI shared handle table. So the other interesting member of the GDI handle entry table is the entry data lookup table. And the entry data lookup table contains 256 pointers of lookup entry address data structure. And each lookup entry address data structure contains 256 pointers of lookup entries. 256 entries of lookup entries data structure. And actually the lookup entry contains the address of the newly created GDI object and a push lock. Now here is a graph that shows us how these data structures are related. And so as I said earlier, we have the GDI handle manager, which is the core data structure, the entry directory pointer. The entry directory contains 256 pointers of GDI handle entry table. Each entry table has the shared memory cell data and the entry data lookup table. And the entry data lookup table contains 256 pointers of lookup entry address. And each lookup entry address contains 256 lookup entries, which have the push lock and the GDI object address. So please try to keep in mind the relation, especially between those two. You can also think them as there are a double array. Oops. So every NTGDI creates something system call, allocates a GDI object, and returns a handle for that object. The last 3 bytes of that handle identify the object type, and the other 2 are actually indexes to the handle table. So as you can see, the 3rd byte is actually the type, and the other 2 are indexes actually to that page table. And we can think those data structures as a page table, and each newly created object lives in the lookup entry directory. So each GDI object starts with an object header. The 2 most significant members of the object header are the handle manager and the TID. The handle manager is actually the handle that we have received from the system call that created that object. And the TID is actually the address of the K-thread data structure, which is actually the data structure that depicts a thread, and it contains the address of the data structure that created that GDI object. Please keep in mind that it's significant the fact that the address of the K-thread is on the object header, because once we have read-write primitives and we can read the heap, we can actually leak the address of the K-thread, and from there with read-write primitives we can actually get the system token, right, and replace it with our user token. So the GDI handle manager uses the insert object internal in order to insert an object to that table that I've showed you. And here are some interesting actions that that function does. The first one is the initialization of the object header, as you can see the TID and the handle manager. And the other one is the initialization of the lookup entry. So it initializes the lock with the value 0 and the GDI object address with the address of the newly created object. So let's see the palette primitive. So the palette is a GDI object that is abused in Redstone 3 for read-write primitives. And it is also used in my exploits to obtain read-write primitives and in order to get the system token. And it was presented by Saif at DEF CON 2017. Now, every palette contains a couple of entries. Every entry is described by the palette entry data structure. And in order to create a palette, we should first allocate the log palette data structure, which is the following, and set the version of the palette and the number of entries. So here's an example of how we can create a palette from the user space. So first we allocate the log palette entry, data structure, sorry, plus the size of the palette entries. Then we set the version and the number of the palette entries. And then we call the create palette function with the log palette data structure as an argument, right? And the create palette is supposed to return the handle for that newly created palette. So here is how the palette looks in memory, in heap, for example. As every other GDI object, it starts with an object header, right? And the other two most significant members are the C entries and the pal color. So the C entries are actually the number of how many entries we have in this palette, and the pal color is a pointer that points to the address space that contains those entries. So here is an example of how we can read the entries from the user space. So we call the get palette entries with the handle of the palette as a first argument, the number of how many entries we are about to read, and the palette entry data structure, right? So as I said earlier, the get palette entries is going to read the entries from the pal color pointer, right? Likewise, in order to set a palette entry from a user space, first we set the palette entry data structure, and then we call the set palette entries with the handle of the palette and the numbers of how many palette entries we are going to set with the data structure of the entry. And as I said earlier, this function is going to write that entry that we have provided from the user space to the palette, to the pal color pointer of the palette, right? So how can we obtain read-write primitives? First, we should spray with palettes in the heap in order to arrange them back-to-back in the heap. And then we should override the pal color of, say, palette A to point to the address of the pal color of palette B. And here is an example to make things clearer. So we have the palette A, and the pal color member of palette A, it's overwritten by a heap overflow to point to the address of pal color of palette B instead of pointing to the palette A's entries, right? So once we do that, we can write any data to any address by calling the set palette entries function with handle of palette A to set the pal color of palette B, and then we can write any data to that address by calling the set palette entries with handle of palette B. Likewise, once we do that, we can read from any address by calling, again, the set palette entries with handle of palette A to set the pal color member of palette B. And then we can read from that address by calling the get palette entries with handle of palette B. So I hope that it's clear. So let's see the mitigation. So as you may know, before a GDI object is used, a reference of that object takes place by increasing the reference count, and afterwards a dereference takes place. So for example, set palette entries is going to call the serlog check with the handle that we have provided from the user space that will find the lookup entry and will reference the object by increasing the reference count. Afterwards, the set palette entries will call the set entries function that is going actually to write the entry that we have provided from the user space to the pal color address. And afterwards, dexref count will dereference the object by decrementing the reference count. So here is the pseudocode of set palette entries. As you can see, it calls the serlog check with the hpal, which is actually the handle that we have provided from the user space. And the serlog check is going to find the lookup entry, will reference the object, and will return the address of the palette. Then in set entries, we are going to write the palette entry that we have provided from the user space to the pal color of that palette. And then in dexref count, we are going to dereference that object. So the serlog check finds the lookup entry from the argument that we have provided from the user space, acquires the lock in the lookup entry to make the reference of the object thread safe, then reference the object by incrementing, the reference count. And here is the odd thing. Instead of just releasing the lock, since we already have the lookup entry, it goes through the object header of the GDI object, fetches the handle of that object, and does the search once again in order to find the lookup entry, and then releases the lock from that second lookup entry. So here's the pseudocode to make things clearer. So as I told you, the handle actually contains the indexes. So the serlog check takes the handle that we have provided from the user space, breaks down that handle to get the indexes, then based on those indexes, finds the lookup entry, then acquires the lock from that lookup entry, reference the object, and then instead of just releasing the lock from that lookup entry, it goes through the object header, fetches the handle, breaks down that handle to get the indexes once again, finds that lookup entry once again, and releases the lock from that second lookup entry. So in case of a heap overflow, the argument handle that we have provided from the user space is going to be different from the one in the object header, which lies in the heap. So in case of a heap overflow, we are going to release a non-acquired lock, making the lock in the lookup entry decremented by 1. And as you recall, the initialized value of the lock is 0, so the lock is going to be equal to 0 xffff. Afterwards, the set palette entries, as you recall, is going to call the set entries to write the entry to the pal color. And later, the dexref count will try to acquire a lock with value of 0 xffff, and our thread is going to deadlock there. So here is the pseudocode of dexref count, which is the function that is responsible for dereferencing that object. So as you can see, dexref count goes straight through the object header, fetches the handle, breaks down that handle to indexes. Based on those indexes, finds the lookup entry, and acquires the lock to that lookup entry, dereferences the object, and releases the lock. Now, as you recall, in case we have released a non-acquired lock due to a heap overflow in ser lock check, we are about to acquire a non-acquired lock with value of 0 xffff, and our thread is going to deadlock here, right? So far in exploitation, we used to spray with a primitive and allocate holes between them, and then allocate the vulnerable buffer to one of the holes, and then overwrite the next object. But with this mitigation, we are going to corrupt the handle manager of the object header, right? For example, of palette 2 in this example. And so, as a result, when we try to call the set palette entries with the palette 2 handle in order to use our primitive, we are going to get a deadlock. So in order to overcome this mitigation, I tried a couple of approaches. I actually found a technique that works in RS2, RS3 that I will explain in detail later. So once I finished my exploit, a couple of weeks have passed, and the bug was reported to GDI by Sebastian Appel. And in October, the same guy released a blog post introducing another technique which had a deadlock. So let's see that technique. So as I said earlier, the set palette entries is going to call the set entries and then might deadlock in dexref count. So we have one arbitrary write. We can use that write to corrupt the next object in the heap with a valid handle this time. And then, since our thread is going to deadlock, from another thread, we can use that next object as a read-write primitive. Of course, after that, our exploit process will not be able to terminate, since it has a deadlock thread, the first thread, right? So here's a graph to make the things clearer. As we can see from the palette 2, we call the set palette entries, and we actually overwrite the palette 3, which is the next object in the heap, with a valid handle this time. But our first thread deadlocks here in the set entries. So in order to understand how to solve this problem, we should take a deeper look in the push locks, how the push locks works. So a push lock looks like a spin lock in a sense that when we acquire a push lock, the value of the push lock becomes 1, and when we release it, it goes back to 0. So the k-thread data structure has an array of lock entries, and at each entry, the address of an acquired push lock is going to be stored. So for example, the x-acquire push lock exclusive x, which is the function that will acquire a push lock, will store the address of the push lock to the lock entries of the k-thread, and then we'll set the first bit in the push lock. Now, in case our thread is already, the value of our push lock is already set, which means that the push lock is already acquired, xf acquire push lock exclusive x will be called. And here is the pseudocode. So as I said, we obtain the lock entry from the k-thread data structure. We set the push lock, we store the push lock to that lock entry, and then we try to set the first bit of that push lock. And in case that first bit is already set, which means that our push lock is already acquired, xf acquire push lock exclusive x will be called. So as you recall, in dexRF count, we try to acquire a push lock with value of 0xffff. Now, the value 0xffff seems like an acquired lock, right? So in our case, xf acquire push lock exclusive x will be called. So going back, we are going to call the xf acquire push lock exclusive x, since our push lock value is going to be 0xFFF. So xf acquire push lock exclusive x creates a wait block. A wait block is a data structure that keeps the waiters linked until the push lock is released. It's the following data structure. Now, depending on whether we are the first thread that will wait for that push lock, our wait block will be set accordingly. For example, in case we are the first waiter, the last member of the wait block will be set and is going to contain actually the address of the wait block. Otherwise, the wait block next member will be used in order to create a linked list between the wait blocks. Now, as you recall, in our case, our push lock has a value of 0xFFF, and xf acquire push lock exclusive x checks if the second bit is set to that value, and if it is, we'll set the wait block as there are multiple waiters. So the address of our wait block, after that, the address of our wait block is going to be stored in the push lock. So now our push lock, instead of having a value of 0xFFF, is going to have the address of our wait block. Then k wait for single object will be called, blocking until our push lock is released. And here is a pseudocode of that as well. So as I said earlier, in case we are the first waiter, our wait block last will be set and is going to contain the address of our wait block. Otherwise, the wait block next member will be used to create a linked list between the waiters. And after that, our push lock is going to contain the address of the wait block as value, right? And then the k wait for single object is going to be blocked until the push lock is released. So to wrap it up, our deadlock thread has two lock entries set in the k thread data structure. The first entry is the one that we acquired in the share lock check that contains the address of the valid push lock. And then, as you recall, we released a non-acquired lock, and we tried to acquire that lock in the dexRF count. So as a result, the second entry of the lock entries will contain the address of the push lock that has a wait block as value. And this wait block is set as there are multiple waiters, right? And here is a graph that sums up what I said. So the first lock entry in the k thread has the push lock of our object, which contains the value 1, because we just acquired that lock. While the second entry we have a push lock that has a wait block as value, and this wait block is set as there are multiple waiters. So our plan, in order to wake up the deadlock thread, is to set the wait block as there is only one waiter, and then release that wait block. That should be enough to wake up our deadlock thread. So in order to understand what's going on behind the scenes, let's study how the release of a push lock works. So the x-release push lock exclusive x will decrement the value of the push lock by 1. And if the second bit is set to that value, the xf try to wake up push lock will be called, trying to wake up any waiters in the wait block. Then x-release push lock exclusive x will loop through all the lock entries to find the one that contains the push lock that we are about to release. And if that entry wasn't found and lock entries in the k thread aren't exhausted, we are going to get a kernel panic because we can't release a lock that we didn't acquire from that thread. As you recall, our lock is acquired from the other thread, the deadlock thread. And here is the pseudocode of the release push lock exclusive x. As we can see, we decrement the value of the push lock by 1. And if the second bit is set to that value, xf try to wake up push lock will be called, and we'll try to wake up any waiter in the wait block. And then we are going to get the its lock entry from the k thread, and we are going to loop through all those entries in order to find the one that contains the push lock that we are about to release. And if that push lock wasn't found and the entries aren't exhausted, we are going to get a kernel panic. So in order to wake up our deadlock thread, we are going to use a palette entry to do the following steps. So the first step is to read the heap in order to read the DID object of the object header, which contains the address of the K thread of the deadlock thread. Then we are going to read the second entry from the lock entries to get the address of the push lock that has the wait block as value. Then we are going to clear the flags in the wait block and set them as there is only one waiter. Then we are going to set the last member of the wait block equal to the address of the wait block, and the next member equal to 0. Again, as there is only one waiter. Then we are going to read the first entry from the lock entries to get the address of the valid push lock, and we are going to set the value of that push lock to 0, as there is none acquired. And then we are going to set the auto boost entries exhausted flag in the K thread. So we can release a lock that we didn't acquire from that thread. And then we are going to call the set palette entries with the handle of the object that we have corrupted. And as I said earlier, the set palette entries will call the share lock check that's going to wake up the waiter. And let's see how. So as I said earlier, the share lock check breaks down that handle to get those indexes. Based on those indexes, finds the lookup entry and acquires the lock from that lookup entry and reference the object. And then from the object header, we receive the handle to find the second lookup entry. But this time, our second lookup entry will contain the wait block, as there is only one waiter, right? So when we will release that lock, we are going to wake up the deadlock thread. So I'll show you a demo of that, but I'm not going to use the patch that I've discussed in the beginning, because my bug was patched in RS3. So I wrote a driver that imitates that bug to show you a working exploit in RS3. So let's see that. So So here we are as a simple user in a Redstone 3 Windows 10. That doesn't work. Let me try to recover the snapshot. It is going to take a while. I don't know what happened there. So it's going to take a while to recover. Oops, wait. Okay, so here we are in Windows 10 RS3. We are as a simple user again, and we are going to execute our RS3 exploit push lock. This exploit is going to be executed as with low integrity. And as we can see, the first thread, as I said earlier, sprays with palettes. Then we issue the vulnerable IOCTL, that is like our heap overflow, that is going to overflow the next palette in the heap with a random handle. Then we are going to call the set palette entries for each palette that we have created. And we are going to overwrite the next object in the heap with a valid handle this time. Then our thread is going to deadlock. Then from another thread, we are going to do the stems that I've explained before. So we are going to read the heap to get the address of the K thread from the TID member. Then we are going to read the second entry that has the push lock that contains the wait block that is set as there are multiple waiters. Then we are going to do the actions to set that wait block as there is only one waiter, right? And then we are going to set the auto boost entries and call the set palette entries or get palette entries that is going to call the shell log check to wake up the thread. Then, as we can see, our thread 1 is awake, and it replaces the system token. So we go the system CMD shell. Let me change the font. So as we can see, we are system, and we can actually this time, I don't know if you guys followed the previous exploitation technique of Sebastian's, but you were actually not able to terminate your exploit, and as you can see, I did that. So let me load the snapshot of the next demo, since it's going to take a while again. Cool. So back to the presentation. So yeah. So back when I wrote a proof of concept for the bug that I found, I was aware of this deadlock technique, but that wasn't an option for me. I was actually trying to come up with a fully working exploit. So my thought was that I thought that since all the handles are known, right, I should try to free a GDI object and then allocate the vulnerable buffer at the same space. With this way, I'll be able to know beforehand the handle of the next object in the heap. So I'll be able to override the next object with a valid handle. So I will avoid all the deadlock stuff. Of course, that didn't work because of the delayed free list. So as you know, X-free pool with tag is called to free a heap block. And that block might not get freed directly. Instead, it's going to get stored in the delayed free list. And the list can store up to 32 blocks. And after that, we'll free them all and start storing blocks again. I guess it was an old mitigation of Microsoft for the use after freeze, but I'm not sure though. So here is the pseudocode of that. X-free pool with tag is actually a huge function. That's only the part of the delayed free list. So as you can see, once you reach the 32 blocks, the XDereferred free pool is going to be called to free every block in that list, in the delayed free list. Otherwise, our block is going to get stored in the delayed free list. So here's my technique. Suppose that we need to overthrow a buffer of 420 size, okay? So we should first allocate 32 palettes of a different size, then spray with palettes of 420 size without holes, and then free just only one 420 palette, and then free the other 32 palettes of a different size. That will make sure that our 420 palette is actually freed and it's not stored in the delayed free list. And after that, we are going to trigger the vulnerable IOCTL that will allocate the vulnerable buffer. And hopefully this buffer is going to land on the same heap space that our 420 palette was. So with this way, we are going to be able to know before the next handle of the palette in the heap. And here is the pseudocode of the technique. So as I said earlier, first we allocate 32 palettes of a different size than the one we are interested to overflow. Then we are spraying palettes without creating any holes of the size that we are interested. Then in our IOCTL input buffer, we set the handle of the next palette in the heap. Then we delete the previous palette, so we free that space. Then we free the other 32 palettes of the different size. And by calling the IOCTL, we are actually going to overwrite the next palette with a valid handle. So I also made a small graph to make things even clearer. So here we are spraying with palettes with 420 palettes without having any holes. Then we free just one and the 32 palettes of a different size. And our vulnerable buffer should claim the same heap space of the palette 2, which is the palette that we freed. So we are going to know the handle of the palette 3. So I'm going to show you a demo again from the same vulnerable driver that imitates the bug that I found. I don't know if the snapshot has fully recovered, so let's see. Yeah, so I'm spraying with 420 pallets. I allocate 32 pallets of different size. I free just one 420 pallet, then the other 32 pallets of the different size. And the buffer is allocated in the same heap space. So I know beforehand the handle of the next pallet. And then I use that next pallet as a read-write primitive. So as you can see, I gotta get a CMD with system permissions, with system token, I mean. As you can see. Right. So privilege escalation exploits are on the rise because of the sandboxes, right? So the Win32k component introduced the Win32k filter to cut down the attack surface. So our read-write primitive should be reachable from that Win32k filter. And in order to understand the Win32k filter, we should take a deeper look in the system call handler. So the system call handler is actually initialized in the initialize boot structure function by writing the address of the system call handler to that MSR register. And once we do that, when we execute the syscall instruction from any 64-bit program, the system call handler is going to be executed. So the system call handler gets the service table from the service descriptor table, and later on, from that service table gets the offset of the system call based on the system call number. And then by adding that offset to the service table, we actually get the address of the system call. So for example, for anti-system calls, anti-system calls exist in the service table in the service descriptor table. For the GUI processes, the W32P service table in the service descriptor table shadow. And for a restricted GUI process is the W32P service table filter in the service descriptor table filter. So let's take a look of the system call handler pseudocode. So when we are going to call the system call handler from a sandbox process, which uses the Win32k filter, we are actually a restricted GUI thread. So we are going to use the service descriptor table filter. And from that service descriptor table filter, we are going to get the service table. And then by using the system call number, we are going to get the offset for that system call. And then by adding that offset to the service table, we are going to get the actual system call address. And then we are going to execute the system call. So suppose that we want to call the system call NDGDI get region data from the sandbox of Edge. So the system call handler is going to read that offset from the W32P service table filter, and then we'll add the offset to the service table filter, and is going to update the stub GDI get region data. So the stub and every stub function is actually a wrapper for the real system call. Every stub function is going to call the isWin32k syscall filter to check if that system call is filtered or not. And if it is filtered, it might lock the action and terminate the process based on some settings. So here is the pseudocode of a stub function. Every stub function pretty much looks the same. So it calls the isWin32k syscall filtered with the number of the system call. And if it's not filtered, the real system call is going to be called. Otherwise, we are going to log or terminate the process in the end-user Win32k syscall filter stub. So every restricted GUI process has a group of system calls that are filtered. The groups are actually split in levels. And for example, the default filter level for the Edge browser is 5, the 5th level. So the PS get Win32k filter set returns the filter level for a current process. The level actually exists in the eProcess data structure in the member Win32k filter set. So there is an array of bitmaps for each level, and we are going to actually use our filter level as an index to get the bitmap for our current Win32k filter level. And based on the system call number, we are going to check in that bitmap if the system call is actually filtered or not. And here is the pseudocode of the isWin32k syscall filtered. So we get from the ps get win32k filter set the filter level. We are going to use that filter level as an index to get the bitmap for the current win32k filter. And then based on the system call number, we are going to check if that bit is set in that bitmap. And if it is, the system call is filtered, right? So I wrote a PyKD script based on that algorithm that outputs all the filtered and allowed system calls for each level. So let's execute it in RS3. So the script takes 3 arguments. The first argument is the from level, the other argument is the to level, and the third argument is the allowed or filtered. So since we are all interested in the edge system calls, the first 2 arguments are going to be 5. And the third one is going to be 0. So as we can clearly see, there are 359 allowed system calls for the 5th level, right? So we can create multiple GDI objects from the edge sandbox, as you can see. But as you may notice, the palette primitive is absent from the list, right? So we need another primitive in order to write an edge sandbox escape. So let's investigate the characteristics that we are going to need for a new primitive. So as you have seen in the palette, it would be nice if our primitives could have a pointer that points to a buffer that we can actually overwrite and read-write that buffer from the user space by calling a system call. Some other GDI objects have an array instead of pointer, and those can be abused as well if we overwrite an integer that acts as an bounds integer, as an integer that defines the bounds of this array or the offset of the array. So those GDI primitives can be abused as well. As I said earlier, the creation and the use should be reachable from the Win32k filter. And since the Windows RS4 will be released in the next month, we should be able to call our GDI primitive from the Win32k filter of RS4 as well. So let's execute our script in RS4 to see what's changed since RS3. So by executing the same script with the same arguments, we get that there are 271 system calls. So the number of the system calls has been decreased by 78 in RS4. And all the GDI objects have vanished from the edge Win32k filter, which means that we can't create any more directly GDI objects from the edge sandbox. But what about other sandboxes? For example, the font driver.exe, which is the font parser that used to live in the Win32k and now lives in the user space in the sandbox process, uses the third level of the Win32k filter. And from that Win32k filter, we can actually create a palette object. But the question is, are we able to use the palette primitive in Redstone 4? And the quick answer is no. The palette primitive and some other GDI objects changed in RS4. What happened is actually the same mitigation that used in bitmaps in the transition from RS2 to RS3, actually now applied to palettes and to some other objects. So the Windows 10 RS4 introduced a mitigation called type isolation. The idea is to isolate the data structure that contains pointers, like the object header and the body of the GDI object, from the entries, which is the pal color, for example, in our case, in palette. So let's see how the type isolation works. So for example, the Win32k filter allocates a section object for each GDI object type and maps it. And as a result, every object metadata for its type is mapped to a different isolated address space instead of the session heap, while the regular entries like the pal color entries in the palette are actually mapped in the regular session heap. So every object type that uses that mitigation allocates a type isolation data structure, which is the following. It contains a double linked list of C section entries. I'm going to explain the C section entries soon. And every type isolation is stored in a global array called type isolation, which has type isolation data structure for every object type that uses the type isolation mitigation. Now, the C section entry is a data structure that contains the section object that we used to create that isolated address space, the address of the isolated address space, and the bitmap. The bitmap actually describes the number of how many available entries exist in that isolated address space. So, for example, for palettes, the section maps an address space of 0x9000 that can hold up to 0x100 palettes, since every palette has a size of 0x90. And once we reach 100 palettes, a new C section entry is going to be allocated with another section object that will create another isolated address space for palettes. Now the palette is using the second entry of the GP type isolation. And actually in RS4, every palette is allocated by calling the C-type isolation allocate type function, while the pal color buffer, which contains the entries, is allocated on the regular session heap. And here is the small pseudocode that shows us exactly that. So here is the bcreate palette, which is actually the function that will allocate the palette. And it calls the C-type isolation allocate type with the type isolation data structure as an argument that's going to allocate the palette data structure in the isolated space, while the pal color, which are the entries, are still allocated in the regular session heap, right? So after spraying with palettes in RS4, we observe that each new section is allocated at 0x10,000 at every 0x10,000 bytes, which means that the first 0x9000 will contain actual palette entries, while the next 0x7000 will be unmapped and will remain unmapped. So here is an example. As we can see, a new C section was created here, and the first palette entry in that section is allocated in BB4 zeros, right? And after an allocation of 0x100 palette entries, a new C section is allocated, and the new palette is going to be allocated in the BC4 zeros, while the last one was in BB8430, which means that there is a 0x7000 gap there. Please also note that the difference between the palette address and the pal color address, because the pal color is still allocated in the regular session heap, while the palette is still it is in the isolated address space. So closing the future of GDI objects, the objects like bitmaps, brush and pens, palettes and fonts and paths are actually using the type isolation, while the other GDI objects like region and some other are still allocated as a whole in the heap. So we can still abuse those objects in order to obtain read-write primitives. And that was the talk pretty much. Thank you.
Any questions?
Do you have any questions? I guess not. Okay.
Thank you.
Thank you.